Okay, let's start. Uh, Today I'd like to talk about how machine learning could help musicians. So first, let me introduce myself a little bit. I'm a graduate of Novosibirsk State University. My name is Dmitry Beloglazov. I graduated about 10 years ago. I studied maths and computer science. Currently, I work mainly as project manager at a freelance team, and I have some very basic machine learning knowledge. But that's not the whole background that I have. I also orchestrate, compose music, record, perform, sing, play various instruments, as you can see. And I also write songs. So before we move on to the next slide, tell me what kind of audio format you think is the most popular. So when you think of music on the computer, what kind of files do you think of? MP3, yeah. So that's the most popular format. And let's jump to the next slide. So first of all, I'd like to give a very brief introduction to two types of digital music, so to say. So there is audio and MIDI. Audio is so. First of all, what is the sound and the music? It's basically the air pressure variations. So the air vibrates, and we perceive it with our ears, and we hear it. Somehow, our brain interprets this, but in the end, this is just the air pressure variations, and so if you before the computers era, there were recorders like tape recorders or something like that, and they basically converted the air pressure variations to some other variations of voltage variations and something else. So what audio stands for in computers, digital audio, well, basically it's the converted variations of the air pressure into a digital representation. And it's sort of an approximation. It's usually it's compressed like MP3. It's a compressed format. The most common format used for recording is WAV, and it's closer to the original signal. It's not so compressed as MP3, for example. But there is one other format which is very important, but it's not well known by common users, so to say. It's MIDI, and you might have heard about it. It's also quite popular, and especially it was popular like 10 years ago on old phones. You could download a ringtone in MIDI format. So what is MIDI? MIDI stands for Musical Instrument Digital Interface, and it's sort of a musical score for computer. It's like so when a musician plays music by just by paper, he sees the notes, he sees the instructions, and so MIDI is the digital format for these instructions. It contains the instrument information, note start and duration information, note pitch, note velocity, like how hard the key should be pressed, etc. So actually, there is a picture here. It's not a very good representation of audio and MIDI. The next slide represents it better. So this is how audio and MIDI look inside a couple of popular music editors. So on the left we see audio. It's the waveform. Basically, it represents the amplitude of the signal. So it's on this axis, and this is time. So we have some maybe a phrase or something like that. So it starts from silence, then it goes up, it goes louder, then it goes down, then the peak is here, and then it ends with silence again. And this one is spectrogram. It presents the frequency. So here we have low frequencies at the start, and then it goes higher. So maybe it's a kind of phrase. The MIDI looks completely different. By the way, if you look at some song, you'll see it doesn't look like this. It's more it's like it goes like one piece. It's not divided like this, so it looks more like a phrase. And here's the MIDI. It's a piece of music that I worked on. It's the piano part, and as you can see, we see the piano roll here, the keyboard, and it's just for reference. For the musician who works on this, and we see the notes. So we see where the note starts and how long it sounds. So these are the notes, and we see at the bottom special information is velocity, how hard the virtual instrument should press the key, or I don't know, hit the strings or whatever. So here's how it looks, and it's just another view of what you see in the music score in the sheet music, and I'll show it to you later. So in my examples, and let me quickly get back and explain why I started this presentation at all. So my goal is to maybe raise the interest to problems that modern musicians have, and how I see the neural networks and artificial intelligence can be helpful to resolve these problems. So in my problems, I usually work with MIDI to compose music, and audio is for recording live sound like vocals, guitars, etc. And so I suggest to use MIDI to solve the problems that I have, and you'll see a little bit more why. But first, I'd like to cover very basic reasons why I think we should choose MIDI. First of all, MIDI is significantly less data. MIDI is an instruction, and it's a little bit silly to compare MIDI files to, for example, MP3 files, because they have very different meaning. But MIDI is still it's like comparing a program and an output of that program. That's so the MIDI is just an instruction. And also, MIDI is more natural. Composers think in terms of music score, not waveforms. So here's the picture of Bach, and that's MIDI too. That's the old representation of MIDI, so to say. So let's quickly jump into what a piece of music is. So I'm going to open this link. And actually, I have it here. So there are basically, so to say, three types of music you can encounter. So the simple one, when you sing in your shower, you sing the melody, something that you sing with your voice. You can sing only one note at a time, and it's also called monophony. So let me play this melody for you. Okay, so that's the well-known Russian song, New Year's song, and it's just the melody. It's just one voice, and that's it. Of course, most of the music that you hear nowadays is different. It doesn't only have the melody, it also has the harmony, something that accompanies the melody. And any pop song you listen to, any rock song or whatever, any classical music, most of them, they have the melody and the accompaniment, the harmony. So here's the example with the harmony. It's very simple harmony. It's just a sort of right hand and left hand. Left hand plays very simple chords. Okay, it sounds better this way. And so I've just put some representation in text of these chords. This will help us in the future. Finally, I'd like to touch one more type of music, so to say. It's polyphony. It's when you have sort of independent voices. Sort of, because they can be really independent. Otherwise, it would be not polyphony but cacophony. So I'll just play. All of these examples, I just created them like yesterday to illustrate the ideas. And so let's take a listen. So two sort of independent voices, still they sound consonant. Okay. So where we are. Okay. So how exactly? So what are the tasks that I see for machine learning here? So the first and the simplest task that you probably already thought of is the generation of new melody. So just one voice, just simple melody. We could learn based on a given data set, and there are many good examples of big data sets, like, for example, traditional songs, and they are usually represented as tunes, as one voice melodies, and we could generate melody based on that. That doesn't look like a very complex task, but it's also not very useful, because with just my melody, it doesn't sound very interesting. So another task we could, another potential task for machine learning, is compose a polyphonic piece of music. And as far as I know, there were certain studies in this field, and there was a project called Deep Bach, and they were able to generate Bach-like music, which was very similar to Bach. So let's take a listen. And so on. So it sounds very good, and that's sort of this problem solved. Still, I'm sure there is more to review here and to research. So, but the actual task that I faced in my music life is how do you compose a solo based on a given harmony? So when you have a set of chords, when you have the background for your music, how do you create a vocal part or a guitar solo that would sound nice? So let me illustrate this again on the little fruit tree sample. So let me jump back to the original example. So let's use the same harmony. This part will stay the same, but what if we could generate something new? Let's take a listen. What could it be? And that's very useful. Sometimes you have to create, as I said, a solo. And when you are running out of ideas, you could use the help of a neural network, of artificial intelligence. But this is a more complex task, of course, because I think if you just apply it straightforwardly in a straightforward way, it would probably be hard to learn for it, and it's better to add some restrictions and somehow teach it how to understand the scales, harmonies, and basically how to lead the voice, how it should sound naturally. So here's another task that I see. It's a sort of a reverse task. It's an opposite task for the previous one. Sometimes you have a melody, but you need to create a harmony for it. This is very typical for folk tunes. I played with a folk band, and sometimes they just harmonize the melodies not the way they were harmonized originally. And in case of folk music, it's very hard to track the original actually. So here's another example. So let me play our third tree with a different harmony. You know the melody, but let's take a listen how it sounds with a completely different harmony. Okay, this sounds a bit jazzy because it uses the seventh chords. It's one of the options of harmonizations. These chords they sound good with this melody, but the other possible options are endless, and it would be interesting to know and to see what the artificial intelligence could come to. So, and the sort of the most complex task for music that I see for neural networks is the automatic orchestration. Maybe it goes even beyond neural networks, because this is a very complex task. When a composer composes a piece of music, usually he writes in piano, and in the end he has the piano piece, like left hand, right hand, and a melody, for example, a voice. If you look, for example, for Notre Dame de Paris musical score, you'll find the only so-called clavier. It's the piano and voice, and there is no orchestra score. So there is no score for violins, trombones, etc. And it would be nice to. I had to orchestrate a couple of music pieces, and it's a very hard task. You have to basically transform one voice with harmony into, for example, 8 voices. And it would be very nice if it could be automated. Still, it's a very complex task, and it goes beyond machine learning, I think. And finally, a couple of other examples that I'd like to cover. It's originally I didn't plan to include them, but still, as a songwriter, I have big troubles with writing lyrics. And it would be nice if we could create lyrics in style of certain poets or poems. If we could teach a neural network to create lyrics for us, and that's a rather typical task, and text generation is more popular than the music generation. And even in Yandex, there is an example here. They recorded an album with lyrics generated by the bot after learning on Гражданская оборона lyrics, and they called Neural Defense, Нейронная оборона. That's I'm not going to play it. You can take a listen. That's an interesting topic as well. And finally, that's sort of a side task as well, but it's very interesting because as a musician, when I try to compose something or orchestrate or, I don't know, create a song, when I work for many hours on this, at some point it becomes too hard to understand what if this piece sounds good or bad. So if it was possible to somehow reflect this with some mechanism that could rate your work, that would be great. So if I play my music to an artificial audience, and it would say, okay, this sounds good, and if I play something else, they say, okay, this sounds better. That would be nice. Of course, this is a little bit of putting off the responsibility of the creation, but still it's, and again, it's not only in this case, but in all of the previous cases, I don't think that it's required that the computer writes music for you and you don't take any part in this process. I think it's more like a hint or some inspiration you could have from a computer-based music or lyrics or ratings of your work. So, to summarize, the task that I outlined today for music creation and songwriting and arranging and orchestration were generation of melodies based on some given melodies, some styles, Generation melodies on a given harmony, very typical task. Harmonization of given melodies, orchestration of given melodies and harmonies, writing lyrics, rating songs or compositions or melodies, or any combination of the above. So one piece could generate melodies, another could rate them. So that's it. Thank you for your attention, and let's discuss questions if you have any.
I have a question. Doesn't it seem a little bit like cheating when you're like a musician who knows data science and machine learning, and he's composing in comparison to the some musician who doesn't know it? Are you going to use like in real life machine learning, or what do you think? What's your plans? Are you really applying it or just for fun?
Yeah, it's a very good question. I think so far what I saw in other projects made in this field, I thought they were made just for fun because I didn't see applications. But I know that in the past, there maybe in present too, there was a composer who really used not artificial intelligence, but some algorithms, some machine generated things to compose his music. So and it was okay for him. So it's I don't think it's cheating. As I said, you don't have to use the material created by a computer and sign it with your name. Like it's I created this, so you can be open and say, okay, I'm using some interesting mechanisms to improve my work or to have an inspiration. Also, that's I recall that when I started thinking about all of this stuff, I talked to a professional musician regarding this, and she said, "Hey, Dmitry, that's strange. How about art? Music is art. It's not something that created by machines." Well, I said, "Look, artificial. The words artificial and art, they have the same root. It's the very close thing, and I mean when you create something, when you compose something, it doesn't just go like from heaven. You just sit and record what you hear in your head. No, it's a complex task. You have to follow certain rules. You have to rework. You have to see how it has certain mathematical basis under it. So it's a complex work, and it could be simplified. So that's I'm looking at this as a means for simplifying some things and looking for some inspiration, so to say. Okay.
Did you try to use debugs for different neural network systems?
Not yet. I was planning to, and I'm in process of. The last thing I learned was TensorFlow. Not learned, but sort of reviewed it. But and that's a good question too, because I forgot to mention my potential role in this kind of projects. So, of course, I'd love to just sit and program it by myself, but it would be nice if someone else helps me. And I would be. I have a very solid background in digital music. I know how to produce music, how to record, how to work with MIDI, and I could be a very good collaborator in this with someone who is interested in neural networks and artificial intelligence who is ready to program it, and we could work together. So that's actually that actually was my goal of going here and sharing these ideas.
So, have any idea how to help Dmitry?
Yeah, so if someone is interested, just reach me by email. I'd be happy to do something great.
Okay.
Okay, thank you.
So, other questions? maybe some additional ideas what we can suggest to also to use in music production, music composing.
I completely have just a comment on the issue that you mentioned about analyzing how the music is good. So I think it's some kind of test adversarial mechanism. Yes, as I understand, it can be applied there. So just in architecture, maybe we can use this test. Maybe.
Yeah, maybe.
Oh, I think that's generate adversarial networks is a good architecture for this task, especially because it is useful for producing such kind of something new melodies which are based on those who is well known, and AI adds some creative creations.
Variations.
Okay, thank you, Dmitry.
Thank you.
So, and we are going to our next reporter. Who's next? Timmy? Boris?
Yeah, I'll be the next.
Understand?
Микрофон не подключен. Вот этот.
А,
Работает? Раз. Раз. Не работает.
Ну, вы с Дмитрием проверяли на...
Раз. Давайте попробуем. Сейчас. У нас немного. Это странно. Так.
он выключен. Он выключен просто. Ага.
О. Раз. Раз. Два, три.
Он все время был выключен.
Да, ну вот так микрофон работает. Так, а здесь нам нужно выключить звук. Как бы его выключить полностью?
Да, ага.
Раз, два, три. Все.
Ну, хоть чуть-чуть будет.
Все?
Okay, so today we're going to continue discussing the fourth chapter of Frontiers in Massive Data Analysis article. So it's about some challenges in massive data analysis, and so we consider real-time data processing. So on the last seminar we discussed data acquisition and data storing. Yeah, it's for you to better to hear me. And today we're going to discuss the the processing of this real-time data. So in processing of real-time data, there are two main stages, or two main approaches, types. So first one is coding, so how to encode temporal data for it to be less to consume the disk space, for example. And so in coding there are two types, it's lossy and lossless. So lossy, for example, is the autoencoder approach, and it wasn't mentioned in this article. I don't know why, because it is from 2013 and I think it should be there, but it wasn't. And so it's the lossless methods, is the Markov models like context tree Wayne method. So we won't discuss these methods, and the whole idea of this presentation is to give just an overview. So when I started to read all these articles about context tree Wayne and other algorithms, I realized that they're too big. They're about 30 pages each, and so they're too complex to understand in just 1 week. So today it will be just an overview. And so the next type is sketching. Sketching, as it's called in this article, is a tool for summarizing temporal data. So it's some kind of representation of this data. So it also has some types. So it's native format, like we can show data with sliding window, for example, just some piece of data, real-time data. And also it's some sampling time series, and also sketching can be in a derived format. So derived format is some applied function to this real-time data, like random projection, histograms, average count, and so on. And of course it's a combination of above types. So for sketching, for example, there is a work of Garoufalakis and Rastolji, and it's presented in the article Querying and Mining Data Streams. So the basic idea here is that we don't work with the real-time data as a whole. We work with its representation. Its representation. So some kind of subsample this data, take this data as a representative subset of real-time data, and then we apply some methods. So for example, the as you can see on the slide, to count an average. So for example, we have a statement, select some aggregate from D is this, where D is odd. So we, if we want to take some average, we take this subsample of our data and count some average, and then we get some representation. So we got 6, but in real it was 7. So in this case, we don't give strict guarantees that we'll get the right result. We just give them some probabilistic guarantees, so that our answer won't be with 90% probability. It won't exceed one interval. So for example, plus minus 1 or something like that. And it's a very big article, so there's not only average, so they also touch a lot of aggregator function, and also they touch a lot of techniques like histograms and how to build histograms basing on this subsampling method. And I think if you're interested in how to do this and how to apply it to real-time, to your real-time system, for example, you should take a look at this article. The next problem that we might face in processing data is that most of the algorithms, they impose linear or some linear memory assumptions, but having this assumption, we cannot really reflect the changes in distribution of our data. So for example, when we get some data stream and it has some distribution that we know after a year or two it may change. So and we should somehow reflect this situation. And in the work of Chiesa, Bianchi and Lugosi, that's called On Prediction of Individual Sequences, they proposed an approach of mixed online and batch learning by FTRL algorithms. So FTRL algorithms, it's follow the regularized leader algorithm. So its basic idea is that predictor is based upon some experts. Experts are some functions that can suggest the further action or maybe not action, maybe the prediction. And in each round of learning a new expert or prediction, a new expert is chosen to that shows the best results upon previous predictions. So it is also quite a big article and it's quite complex to understand. I just found some good video how to show how follow the leader algorithm works. I hope it will work. Or not. We should wait for a while. Or I will reload the computer. Okay, so it will not start. Maybe we should go to YouTube. That was a bad idea. Okay, we'll go further. So no video for today. So another problem that we might face that our input rates they exceed the computer capabilities. Well, for offline learning and prediction algorithms. So in this case, we should, like in the example of these aggregator functions, we should approximate our representation, and that's called data stream approach. The last mentioned in this article works was about Stanford data stream management system, so it's based upon this data stream approach. And there's a book of how to work with these data streams by Mutukrishan in 2005. Yes, so but there is still a major challenge of efficient statistical inference for general models. So we have same problems here, like changes of distribution and so on, that we should face and how to work with it. So if, for example, you see that your computing capabilities are not offline learning and yes, and prediction algorithms they exceed your computing capabilities, so you may want to see this Stanford data stream management systems and maybe, for example, read that book. So yes, again, some lags. We should wait for a while again.
Hang out.
I think we should wait. No, it's okay. Nothing bad. What? No.
What's the program left on Google Chrome?
No. Yeah, this one. What?
This program.
This one? It can be closed?
Yeah, it can be.
No?
Yes.
Streaming it?
Yes.
Okay. I'll close it. Are we sure?
Yes.
Yes.